So let's continue our discussion of two-stage op-amp design. I'm not going to review this stuff. I can't review that because some of the material that's on there we haven't covered yet. So here's an example I was going to go through. Determine the DC open loop gain, the DC closed loop gain, the open loop poles, the open loop zeros, the closed loop poles, and the closed loop zeros. If the characteristic polynomial is 10 to the 7th, and it's got 3 roots, 1 0 and 2 poles for this basic amplifier structure here. So can we get the open loop gain pretty easily? Got to get beta first, right?
Yeah.
And what's beta here?
1 plus R2 over R1.
Nope.
R1 over R2 plus
R1 over R1 plus R2, right?
Yeah. It's not the same as R1 over R2 plus R1.
Oh, you're right. So that's the DC gain. Well, we'll probably have to do some calculations to get the poles. Actually, you can show that the open loop and closed loop zeros, I think, are the same. So the 0 is probably at s plus 1. We have to calculate the poles. So if you go ahead and put in that polynomial, you'll find that this is the transfer function, ABF. And we see the 0 is the same as the open loop 0. The closed loop and open loop zeros are the same. But we see the poles have moved. And the poles then are just the roots of that second order polynomial denominator. You can use quadratic equation to pick that up. So we saw for identical first order low gain stages, if we cascaded 3 amplifiers, beta A naught cubed has to be less than 8. Industry seldom does 4 or more stages. The problems of compensation, the problems of maintaining stability are even more stringent there. So let's consider now a case where n equals 2. So n of 3 is not interesting, n greater than 3 is not interesting, so let's back up and get n equals 2. There's still some room in here between 1 and 2 of picking up some gain. So if we have 2 poles, then the gain with feedback can be written in this form here. And again, I'm going to assume that now P2 is equal to KP1. So without loss of generality, P1 is the lowest frequency pole, and P2 is the scaled version of P1. The characteristic polynomial then, if I multiply through by P1 tilde P2 tilde, is of this form here. We don't have any stability issues here at all. Notice the poles here are all in the left half plane. That's the good news. At least based on this analysis, it appears that this amplifier is always stable. However, I'm going to consider the special case where there are identical stages. So in this case, k will be equal to 1. And I can then find a closed form expression for the poles. And the poles are at minus P1 tilde, magnitude of the pole of the original amplifier, times 1 plus or minus j squared of beta A total. If A total is large, what we have is a very small real part and a very large imaginary part. So these poles are pinned right up on the imaginary axis. It's a lousy amplifier. We don't really care if it's stable or not. The poles are so close to the imaginary axis, you're going to have serious gain peaking and serious ringing. If there's another pole in the system, it'll probably become unstable. Why don't we worry about stability? If you're building an amplifier, you're worried about stability. It's going to have horrible overshoot and ringing, right? So this is a useless amplifier as it stands. You can plot the locus of the feedback poles as a function of k. So when k equals 1, that is when the poles are identical, we have complex conjugate poles up here against the imaginary axis. As we start getting more spread on the poles, the complex conjugate poles start to move to the left, and they eventually come together, and then they split and move along the negative real axis like this. So this is the locus of the feedback poles as a function of k. So we can ask the question, what does K have to be? Now keep in mind, K has nothing to do with the gain. So we might have the same DC gain on the two amplifiers to get a high gain, but we might have different bandwidths on the two. We can adjust gain and bandwidth independently. You can show that if the poles, the second order all pole system, if the poles lie on the 45-degree line, we have a maximally flat magnitude response. That's nice. There's no peak in the magnitude response, and you get maximum bandwidth. You can show that if the poles are coincident on the imaginary axis, when they come down and become a pole doublet, that corresponds to maximally fast time to magnitude response without rating. It goes up as fast as possible, but doesn't overshoot and rain. So when we design amplifiers, we usually design amplifiers so that the poles, if they're complex conjugate poles, are between here and here. The angle they make is between 45 and 90 degrees, and the complex conjugate pole, or the poles, are coincident. We typically don't like to design amplifiers so the feedback poles are out here someplace, widely separated on the negative real axis. Any idea why we don't want to do that?
Because then it's on the real axis, and that means it'll show up.
No.
Can you say the question again?
Yeah. The comment was we usually try to separate the poles so that they lie between here and here, just slightly, maybe barely on the negative real axis or slightly off the real axis, but not any more than 45 degrees up. Why don't we go ahead and, it's easy to make K bigger and push them down here so they're widely separated on the negative real axis as well. Very easy to do that. Any idea why we don't?
Because we don't want to push one pole closer to the right half.
It won't move over. This is like a brick wall bigger than the Trump's wall.
Okay.
And yes,
Quick question. What's the zip code for the card?
50014.
Okay, thank you.
Yes.
Do we want to keep the poles in the same location so that when we go to the voting plot, we get 40 dBs of decade at one point instead of like a 20 and then 40 later?
What's bad with 20 and 40 later?
The designer might want it all to happen right at the same time.
Why?
I don't know.
It'll work great if you make the separation even larger so they're out here. But what's going to happen is your closed loop bandwidth is going to be lousy. You're going to spend a lot of power, and you're not going to get much frequency response out of it. Okay, so you don't want to let the poles go any closer than 45 degrees because you're either going to get peaking or raining or both. But if you push them down here and have them separated very far, the feedback poles on the negative real axis, you're going to spend too much power for the bandwidth you're going to get out of the amplifier. Make sense? So it's a practical issue. They'll work fine, but the power is going to be too high.
I knew that.
I figured you did. So let's look at the condition to have case one, identical negative real axis poles. Here's the poles, and we drive the expression of poles. To put the poles on the negative real axis coincident, we have to make the discriminant 0. Then it'll be plus or minus J0, right? And if we make this discriminant 0, we have 4 A total K beta has to equal K squared. And we can solve that equation and we can see that K has to be 4 beta A0. The pole spread has to be 4 beta A.
So if we have, again, 10,000, we need to have 40,000.
Yeah. That's right. We don't have an A squared or J cubed in here. We've got 4 beta A. So this is the way it is. So if we're going to make this two-stage amplifier work, and we want those poles to not have complex conjugate pairs, it has to be this. If you want to put them on the negative real axis and to separate them, it's got to be even bigger. Okay? So we got one constraint. Case 2, maximally flat magnitude response. Of course, that corresponded to putting the poles at 45 degrees. We get some ringing now, a little bit, but the response is maximally flat. Depends on your application, where you need it. To do this, we have to set the real part, and the magnitude of the imaginary part is the same. Put it at 45 degrees. So we have to satisfy this equation, and we can solve this equation for K, and K is equal to 2 beta A naught. K is smaller. Okay? So we have a small ringing, but notice it's a factor of 2 reduction in the pole spread from what we had before. So if I put those two conditions together, I want the pole to be somewhere between 45 and 90 degrees then. That's equivalent to saying that K has to be bigger than 2 beta A naught and less than 4 beta A naught. Well, this could get bigger, but then our energy efficiency gets bad, right? So these are the conditions we usually set up for designing an amplifier. We put the pole ratio to satisfy this equation. So we're going to talk about compensation shortly. Compensation is that part of the design process that modifies the poles of an amplifier to achieve the desired closed-loop response, to achieve this relationship if it's an all-pole amplifier. Okay. Notice also that the conditions for compensation are strongly dependent upon beta. Now this is kind of an important observation as well. If you're designing catalog part op amps, you want to have your op amp usually, not always, usually go in as many sockets as possible. A company, I don't know how many commercial op amps are available. A number of years ago, somebody said there were 3,000, probably more than that. There's a lot of commercial op amps available. Wouldn't it be nice if you were the leading manufacturer of op amps, you only had to make one op amp, and everybody put that op amp in their sockets? Wouldn't that be nice? Okay. So when you design an op amp, you want to go in as many sockets as possible. That means you usually set the compensation so that for beta equals 1, which is the most stringent condition here, remember beta is always going to be less than or equal to 1, this is the most stringent condition, you design it so it has good performance in the unity gain configuration. That means that it's overcompensated for different gains. If you have a gain of 10, it's grossly overcompensated. That means the customer is spending a lot more power than they need to spend if they're using it in something other than unity gain configuration. Make sense? So if you're building integrated op amps, you find out what your beta is for your application, and you compensate it so that it's designed correctly for your value of beta. And many times you'll save a lot of power. Yes?
But how easy is defining beta in your design?
Real easy. The number polynomial is always 1 plus A beta. So the system designers will dictate what beta is for your circuit. Then the circuit designers have to build a circuit that works with that value of beta. Make sense? Yes?
Have we related K to physical or the practical parameters of our circuit design yet?
Not yet. Not yet. But it's easy to do. We're going to see that K is primarily determined by a size of a capacitor. And that capacitor isn't in our circuit yet. There are some, I was going to have another slide and I ran out of time before this lecture. There are some op amps that are sold that are called decompensated op amps. Decompensated op amps. You looked on the data sheet and it said this op amp is only stable for gains, for closed loop gains bigger than 10. That means don't buy that op amp and put it in UD gain configuration. Why do you think you're doing that?
More power efficient.
More power efficient. If you know you're not going to have using it to gain a 1 and you want to save power, then why buy an op amp that's compensated for unity gain when you're not putting a unity gain configuration? I wonder how much this power savings could be. Quite a bit. Make sense? Unfortunately, or surprisingly, those are relatively unpopular. A lot of people that use discrete component amplifiers just bite the bullet and spend the extra power and use an amplifier that works with a gain of 1 when they have a higher gain on it. Just a note here, this kind of summarizes where we're at. Some amplifiers that are termed single-stage amplifiers in many textbooks and papers are actually two-stage amplifiers. An example is that current mirror op amp. It's usually considered to be a single-stage amplifier. Another example is the cascode structures, telescopic cascode amplifier. We treat it as a single-stage amplifier. It's really a two-stage amplifier. These invariably have a very small gain on the first stage and a very large bandwidth on the one stage. So they behave much more like a single stage amplifier, and that's probably why they're classified as single stage amplifiers. I don't think it's particularly confusing. It doesn't bother me much. I just want to point out that some of those structures are really two-stage amplifiers. So I guess that the only comment I want to make here is it's important we understand how the open loop and the closed loop performance relates before we can proceed with designing our two-stage amplifiers. So let's continue our discussion on two-stage op amps. So here's kind of a picture of a two-stage op amp. It's a really simple concept. And building a two-stage amplifier pretty much involves determining what's in F1 and P1 and F2 and P2. This is for single-init inputs and single-init outputs, or differential input followed by a single-init output. This is a common architecture. Now we have to decide what's in the differential structure and what's in the single-init structure. Notice we have a current mirror connected counterpart circuit on the left part of the differential stage. This is widely used as well. Most commercial op amps are going to have this kind of an architecture. Notice I've got tail current bias in the first stage and tail voltage bias in the second stage. That's commonly done as well. I could have differential outputs. And so here I have, on both the left side and the right side, I have single stage amplifiers with tail voltage bias. Now, when you put a tail voltage bias in, it completely separates the left and the right side, so you can throw away one half of that op amp. And that's why I'm only showing half of it here. This circuit requires a common feedback circuit if we want a differential output on the structure. Here's a fully differential stage both places. Fully differential first stage, fully differential second stage, and I put tail current bias in both places. Usually you don't need tail current bias in the second stage. But it certainly would work. So where are the poles coming from in our op amps? We talked about the poles, but we haven't talked about much about where they come from. Up to this point, we just stuck a capacitor CL on and did a calculation, right? Where does that CL come from? Leave it off in the first place and you don't have to worry about this problem. So let's talk a little bit about parasitic capacitances in MOS devices. First of all, if we have a PN junction, and we reverse bias the PN junction, and for all of our MOS transistors, the drain and sources are typically created by a diffusion of one type material into another type material, and we typically reverse bias that PN junction. We create a depletion region. Anytime a depletion region is created by between two conducting regions, we have a capacitor. So that's a junction capacitor. And the size of this junction capacitor is area and voltage and doping level dependent. And for large junctions, it can be quite large. It's not uncommon to have a first stage of an op amp that might have a width-length ratio of 500:1. If you have a width of 500 microns, you're going to have a lot of area in the drain or the source. There's a lot of area in the drain and the source, you're going to get a lot of capacitance between the drain or source and the bulk underneath. So here's an N-channel transistor. On both the source side and the drain side, we have a capacitance from the bulk to the drain or source. When it's turned off, we have a capacitance from the gate to the substrate. We don't care about that usually because we usually have them turned on. When we're turned on, there's an inversion layer here. There's going to be a capacitance between the gate and the channel. And then there's typically some diffusion underneath the gate. So there's going to be capacitance from gate to source on the left side and a capacitance from gate to drain on the right side. And I call those overlap, CGD-OL for overlap capacitance. And we have the same things present in a P-channel transistor plus one more. If it's in an in-well process, we have another capacitance between the well and the substrate. We could write down expressions for all these capacitors in terms of the area in the perimeter. And if you look at the PDK for any process, they will have the capacitance density of all these capacitors. Okay? So it's pretty easy to determine what these capacitors are. Wow! Every capacitor in a circuit adds one pole. So if you have one transistor in a circuit, you've got 1, 2, 3, 4, 5 or 6 capacitors. And now fortunately there might be a couple of loops in there. So you put one transistor in a circuit and you're already up to, if you consider all of them, you're already up to third or fourth order. You put 2 transistors in a circuit and look at the order, you're probably up to 7th or 8th order. What?
Good luck solving.
Good luck in solving. I'm not going to do a MATLAB calculation of this. I did a MATLAB calculation on a much simpler circuit, and we had pages and pages and pages out. This will be much worse. Is that good or bad? That's bad. So what we do, we just take these capacitors and we model them on top of our model of our transistor. And I should have used a symbol for the small signal model. We take the small signal model and add these capacitors, and this becomes our frequency dependent model of our transistors. Usually CGS is the largest because we have an inversion layer underneath the gate. The gate's very thin. And the channel will extend from the source almost to the drain in saturation region. So we typically lump that gate to channel capacitance as a gate to source capacitance. And that's COX, which is the high density times the area, approximately. So CGS is often the largest. CPB and CBS are often quite large as well. This one here and this one here. The gate drain overlap capacitance here is usually pretty small. And this one here is the sum of the gate drain overlap capacitance, gate source overlap capacitance, and the gate channel capacitance. The gate source overlap capacitance is usually pretty small. It's not a major contributor to that. So here's a 2-stage amplifier. This happens to have 2 tail current biases. And you see that there's a lot of capacitors in this 2-stage structure. is about 5 in each transistor. So that means there's about a 10th order transfer function, minus a few loops. However, many of them appear in parallel. But even some appear in parallel is still quite a large number. If you look at the number of nodes in that circuit, however, there's a small number of nodes. There's a node here, 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 and here. So there's 4 nodes on the drains. And then there's a node here and here, but those nodes are in AC ground typically. So we really only have four nodes that are of concern. And it's the capacitors on those nodes that typically dominate the frequency response of this network. So maybe it's not as bad as it looks. We're down to 4th order. Oh, that's still not too good, is it? So what we're going to do, by the way, if you want to find the poles, and it was a 4th order system, after you get the transfer function, which might take a long time, then you've got to find the roots of that transfer function. And that's a horrendous task. Make sense? So what we're going to do is try to approximate the poles. We're going to solve a 4th order polynomial, approximately. Now, you can show that if you've got a bunch of poles in an amplifier, you're really mostly concerned about the biggest low frequency pole and the smallest high frequency pole. Oftentimes you'll have poles that can be broken into 2 groups: high frequency poles and low frequency poles. Low frequency poles might be in the sub-audio range. High frequency poles might be in the approaching the gigahertz range. There's oftentimes orders of magnitude separation of those poles. So the frequency response of the amplifier is pretty much determined by the lowest high frequency pole and the highest low frequency pole. Make sense? So what we do is we decompose. So we're going to consider the shunt capacitors. We're going to use the concept of a pole on a node. So we're going to assume that there's a one-to-one correlation between the nodes in the circuit and the poles in the amplifier. So we're going to decompose the capacitors into 2 sets. Those capacitors that create low frequency poles and those that create high frequency poles. Large capacitors create low frequency poles. Small capacitors create high frequency poles. So I'm going to label those CLO1 through CLOK and CH1 through CHN. To find the K low frequency poles, what we're going to do is replace all independent voltage sources with short circuits, all independent current sources with open circuits. So we're just looking at a small signal model. All high frequency capacitors with open circuits. And one at a time, we're going to select the low frequency capacitors and determine the impedance it faces if all other low frequency capacitors are replaced with short circuits. So we're going to look at the circuits with one capacitor at a time and look at the impedance facing that capacitor. And then we're going to claim that the approximate low frequency pole corresponding to that node is equal to 1 over the resistance you see facing the capacitor times that capacitor value. So if I do this for all the capacitors, I will find all the low frequency poles. Their approximations are pretty good. If the poles are reasonably well separated, it will do a pretty good job of getting the dominant low frequency pole, the biggest of the low frequency poles. To find the high frequency poles, we again look at the small signal equivalent circuit. We're going to now high frequencies, those low frequency capacitors are looking like short circuits. So we're going to replace all the low frequency capacitors by short circuits. But we're low enough in frequency that we don't see the rest of the high frequency capacitors. So we'll replace the rest of the high frequency capacitors by open circuits. Take those capacitors out one at a time, look at the impedance facing the capacitor, And the high frequency poles then are going to be 1 over the impedance facing that capacitor times that capacitance. So right with me. So now we have an algorithm that allows us to approximate all the poles in this amplifier. Even though they're approximations, they save us the job of solving this high order polynomial and factoring it. It provides closed form analytical expressions for the poles in terms of the components of the network. It provides a lot of insight into what's affecting the frequency response of the amplifier. This loses all information about zeros. If there are zeros in the network, we don't get the zeros, we only get the poles. As I mentioned, we oftentimes refer to these as poles on a node because these are the dominant contributors to the poles typically. So let's look at an example. I'm going to obtain the approximations of the poles for the following circuit. These are both small capacitors. So since C1 and C2 are small, we have 2 high frequency poles. So what I do is I take the capacitors one at a time and replace the other capacitor with an open circuit. Look at the impedance facing them. So when I take this capacitor and replace that by an open circuit, I just see a 1K. And then when I take this capacitor and replace this by an open circuit, I see the series combination of 1K and 5K, which is 6K. So those are the 2 impedances. I multiply those 2 impedances by the corresponding capacitors and I get the pole approximations. And I find that one of the poles is at minus 833 kiloradians per second and the other is at 10 megaradians per second. Okay. If I actually calculate the poles solving this network, I find that I have an 18% error on the high frequency pole, and I have about a 1.4% error on the lower frequency pole. What we say was most important? The lower the frequency pole, the lower the high frequency pole is most important, and in this case we were 1.4% off. Okay? So in one case we do it by inspection, in the other case we do it with pain. So, let's look at compensation now of basic 2-stage cascades. This is how we're going to move the poles around to satisfy the pole spacing criteria or eventually to compensate the amplifier. Ben, how close are we getting?
You got 16 minutes left.
16, okay. So I've got 2 ways to do this. One is what we call internal compensation. I'm going to put a capacitor C1 at the output of the first node. And the other one is called load compensation or output compensation. I put a capacitor on the output node. So I'm adding capacitors to the circuit for the purpose of what? Pulling the poles apart. Okay. Since I'm adding capacitors, I don't affect the gain. So if I've got a good DC gain, I'll still have that gain. Now when I add these capacitors on, what am I going to do to the bandwidth? Going to be reducing it. If that capacitor is very big, I might dramatically reduce the bandwidth. I might dramatically reduce the gain bandwidth product. And if I've got 2 poles that are widely separated, I'm making the amplifier look about like a first order system. Make sense? So one thing's good about it, that is that I'm going to be able to use it now. One thing that's bad about it is I've lost a lot of gain bandwidth product. But we may not have a good alternative. Modest variations of this principle are typically used. So this is the key principle. Internally compensated op amp, since we put a capacitor on this node, oftentimes it has to be big. It creates the dominant pole on the internal node. Output compensation creates the dominant pole on the external or the output node. Output compensation is often termed self-compensated. Okay, that's nice. Means you don't have to compensate it. The idea is, you know you're going to drive a large capacity load. Let that load be the compensation capacitor. But be careful, because if you go back and say, well, I didn't really want to drive that large load, I really wanted to drive a smaller load, then you might have problems. My final comment there is, everything else just details. This is the principle. Everybody understand the principle? We're 3/4 done. But the details take a little bit of time too. Oh, if we're going to build a two-stage amplifier, we have a lot of choices. The first stage, and we can make this list bigger if we wanted to. The first stage, we can use a common source quarter circuit. We can use a cascode, or regulated cascode, or folded cascode, or folded regulated cascode, or a current mirror. We can have differential or singulated inputs. We can have a tail voltage or tail current bias. The second stage, we do the same thing. And then we can have a choice of either doing output compensation or input compensation. Oh, and I have a choice of having P-channel or N-channel inputs on the first stage. And I have a choice of P-channel or N-channel inputs on the second stage. So the question, this defines 2,304 different architectures. That's more than the textbook. Which of these 2,304 choices can be used to build a good op-amp?
What's your application?
Good answer. Depends on the application. Can we X out a lot of these?
It's possible.
No. Yes.
Current mirror's not that bad. We just said it didn't offer many benefits, but if M was fairly large, it wasn't much worse either. And maybe it's got good signal swing characteristics, and maybe it's easy to design. Well, the answer is that all of them can be used to build good op-amps. For some applications, one might be better than another one. So you as an op-amp designer, your first task, if you're going to build a two-stage op-amp, is what? Well, and then decide which architecture you use, right? You only have to pick one out of 2,304. And we can add a few more to the list if you want.
Good thing there's 3,000 kilohertz.
What? That's right. They're double dipping, right? How many of them do I think that I would expect you to be good at? All of them. So our goal. So our goal.
2,304.
Yeah. So my goal is to have you better at some of them than others, but understand the principle that will work for any of them. Make sense? So there's actually a few additional variants. So the number of different architectures is actually quite a bit bigger. We can put a buffer on the first stage or not. We can put a buffer on the second stage or not. We can use push-pull, or there's a. So we actually are looking at tens of thousands of different basic structures that we can use to build op-amps. Yes?
I'm going to dare to ask, what if we went and changed from bipolar, used bipolar devices? Do all of these stay the same?
Absolutely. So that's another factor too.
Right, yeah.
Okay. Fortunately, most people, even though there might be several different structures that they could use to meet a particular application, usually only a relatively small number of these are really talked about very much. We can also establish some rules that provide guidance as to which structures may be most useful. So one thing that's not usually very useful is to have a tail current bias on the first stage and a tail current bias on the second stage. Because the first stage doesn't leave a common mode signal on the output. If there's no common mode signal left on the output, you don't need a good common mode rejection ratio. If you don't need a good common mode rejection ratio, you might as well eliminate the tail current source. So there's a bunch of rules of thumb we can look at that will eliminate some of these structures in applications. So tail current source usually used in the first stage, tail voltage in the second stage. Large gain usually used in the first stage, smaller gain usually in the second stage. First and second stages usually use quarter circuits of opposite type. So usually if you use N-channel inputs on the first stage, you use P-channel inputs on the second stage. Input combo and input range of concern on the first stage, but output swing of the first stage is of reduced concern because you got a big gain on the next stage. Output range on the second stage is of big concern, but not the combo input range. A combo rejection is the first stage of concern, but not on the second stage. Noise on the first stage is of concern, but not much on the second stage. Offset voltage is usually dominated by that of the first stage. Okay, so a whole bunch of observations about characteristics that go into your selection of the architecture. So let's look at an example. Let's look at a common source, differential input, tail current, first stage, common source, single input output, tail voltage bias on the second stage, internally compensated. So that I've just defined an op-amp. So this is a cascade of two op-amps, a popular structure. Another choice might be this: folded cascade, differential input, tail current, and so forth. So here's probably the most common two-stage op-amp. What is it? It's tail current bias, current mirror load, common source input with N-channel devices, driving a common source second stage with a current source bias and a compensation capacitor on the first stage. We wouldn't put that capacitor there if it was going to be dominantly compensated on the output stage. It would make things worse. Yes?
If you use like the common or the source bias, the voltage source bias, does that get rid of a pole? Because
What?
does that get rid of like a pole? Because a pole is
Good question. So we haven't talked about the common mode gain of this yet. There's a capacitor on this node too, but that voltage is at 0 volts in the differential excitation. So that pole is in the system, but it's not in the difference mode transfer function. It crops up on the common mode transfer function. Does that make sense? So we have eliminated a common mode pole by going with the tail voltage bias on the stage. This capacitor on here does affect the common mode gain characteristics, which we will talk about a little bit later. Hence, it affects the frequency dependence of the common mode rejection ratio. When we apply common mode feedback circuits, they are also part of the common mode path. So we also have to compensate the common mode feedback path so that we don't have overshoot or ringing. That is, we're worried about not just stability, but no overshoot or ringing in the common mode path as well.
another capacitor will be added to compensate?
So there are two ways to do it. One, if there's a problem, we have to add another capacitor. Or we won the lottery.
One.
And oftentimes what we find is that the compensation capacitor that we use to compensate the differential path will also compensate effectively the common path. Good question. Oh, there's one pole I haven't talked about. So we talked about this node here. Ms. Elba correctly identified a concern here. We said that for differential operations, it's not a concern, but there is a node here that affects the difference mode gain. But if you look at the impedances on that node, you see, first of all, this capacitor is probably not too big. It's a diffusion capacitance here, a diffusion capacitance here, and two gate source capacitances in parallel. But the impedances are an output conductance here and a GM here. So we've got a fairly small resistor and a fairly small capacitor, which means that it's a real high frequency pole. So we can usually neglect that pole on that node. 5 minutes?
Yep.
Okay. This circuit we can also externally compensate. And it would be appropriate to externally compensate it if you know you're driving a large capacity load. But usually if you don't drive a large capacity load, you prefer to internally compensate it. You know, if you look at this structure has been talked about for 30 years. And there's quite a few degrees of freedom in this design. You've got a bias voltage here, a W over L ratio, that's 2. W over L ratio 3, W L ratio 4, W L ratio 5, bias voltage 6, W L ratio 7, and a compensation capacitor 8. There's 8 degrees of freedom in this design. And maybe only one constraint to make it work. And that's pick the right size compensation capacitor so it has the right frequency response. At least 7 degrees of freedom. Our goal will be to put together a procedure so that you can have a recipe for designing this op-amp. But you'll find other people put recipes together that are different than this. And your recipe will likely affect the performance of your structure. So we only have 7 degrees of freedom. This architecture has been around a long time, but to this day, there's not a universal agreement on how to optimize the design of this op-amp. Does that make sense? Oh, we got a problem. The pole spread that we have to have, beta A1, A2, we get high gain on the first stage here and high gain on the second stage. Beta A1, A2 makes C sub C unacceptably large for on-chip solutions. So if you go back in time to the late 60s up through the early 70s, the way this problem was solved was they put a pin on the package and they say, you must attach a capacitor on this pin. That capacitor is CC. They couldn't put that capacitor on chip because the size of that capacitor was too big. There were many op-amps that went into commercial production that had that extra pin to put that capacitor on. Although some of those op-amps were expensive initially, today we're in a situation where if we did that, the cost of the capacitor may exceed the cost of the op-amp. Okay?
You're disconnected.
Am I disconnected? I think it's pizza time.